Hello and welcome to Calculus Lesson 9. Today we are going to cover a ton of things, so please pay close attention and we will get through this. So first we are going to graph the following on a number line. X is in the real numbers and the absolute value of x minus 5 is less than 2. Again, when we say absolute value, you need to remember that we're talking about the distance from 0. So I'm saying the distance from 0 of your number minus 5 is less than 2. A better way to write absolute value is to consider the two cases, whether I'm plugging in a positive number or I'm plugging in a negative number. If the number inside the square root is positive, it just stays the same. X is less than 7. If the number inside the square root is a negative, then we multiply the entire thing by a negative to make it a positive. So what does that do? Well, if I solve this, it changes the sign. If I multiply both sides by -1, and then I have x is greater than, it looks like positive 3. So if I take these two together now on my number line, this describes all numbers between 3 and 7, not including those numbers. Does that make sense? Well, when we shift this 5 to the right, we're really saying the distance away from 5, instead of before where it was the distance away from 0, this is saying the distance away from 5 is less than 2. Here's 5, and the distance away from 5 is less than 2. You have to know this though, that when you plug in a positive number, this absolute value gives the exact same thing. When you plug in a negative number, so when this is negative, it gives you the opposite of that number. And that's the quickest way to solve those problems. Now, if we have a different set, x is in the double struct z set, which is the set of integers, and the absolute value of 3x minus 1 is greater than 2. Again, the way we're going to solve this is we are going to take the positive option, which is 3x minus 1 is greater than 2, and solve. X is greater than, it looks like, 1, right? If I add 1 to both sides, I get 3. Divide by 3, I get 1. Now, the negative option, if this number ends up being a negative number, then I have negative 3x minus 1 is greater than 2. I'm going to multiply by negative on both sides, so I get 3x minus 1 is less than 2. Remember, you change negative 2. Change the sign when that happens. Then I'm going to solve. So I'll add 1. That's negative 1. So x is less than negative 1/3. Is that correct? Yep. So now what I know, since this is greater than, I know that it's going to point outward because I'm saying the distance away from a number, which just so happens to be 1/3, is greater than 2. So these should now point outward. So I have -2, -1, 0, 1, 2. I want all x's that are greater than 1, remembering that I'm selecting integers. So I'll probably give 3 and put an arrow that way so that it's the filled in dots, but you're not drawing an arrow like we did here or a line over it. And then I want all integers less than -1/3. That sounds like -1, -2, and going on that way. All right? Since I want my absolute value is greater than, it's going to point outward. Here my absolute value was less than, so it pointed. All right, next up. What are the graphs of special functions? So you should know, because you're in calculus now, the graphs of many functions. The first one is a line. Generally, if the slope is positive, your line looks something like that. Now, it might be shifted up and down, it might be steeper or less steep, but that's what it looks like. The absolute value function looks like this. It looks like a V, and it can be shifted left or right, up or down. The negative absolute value, so let's take negative absolute value of x minus 2, it's going to look like this. It's going to be the negative absolute value, so it's a V pointing down, but it's shifted 2 to the right. So it'll look something like that. In case you want the equation of this one, that would be like, let's call it 1, the absolute value of x minus 1. And this could be like y equals x minus 1. Another function that you should know is obviously your sine, cosine, tangent graphs. But what happens if you take the absolute value of sine of x? Well, where your old sine used to go up and down, is this going to work? Nope. Okay. So your old sine used to do that. If you take the absolute value of it, all of those negative parts become positive. So it looks something like that. And that happens anytime you take the absolute value. It's just going to bring the negative parts positive. There are more examples on page 56 of your book that you should review later. All right, the next part of our lesson is that we are going to be introduced to a new function. This is called the step function, or the greatest integer function, less than, sorry. So a step function we'll write as y equals, with a bracket around it, x like that, and it's really, we're just graphing the greatest integer less than x. So it looks something like this. At 0, the greatest integer less than 0, less than or equal to, is 0. For 0.5, the greatest integer less than or equal to 0.5, let's just do that, is still 0. The greatest integer, or integer less than anything but 1, is going to be 0. Any fraction, the greatest integer less than that is 0. Now, from 1 to 2, the greatest integer less than those numbers, well, at 1, it's 1, obviously, because it's less than or equal to. And then it goes all the way to 2, but doesn't include that. Then we go from 2 all the way to 3, doesn't include that, and so on. And so this is the step function. It also goes down here. Like that. So when is this function used? Actually in a lot of different ways. So often we want to round things to the nearest integer. Sometimes we round down, then we would use the step function. All right, and wait, there's more. Next, we're going to add logarithms to your box of tricks. So just as a review, what is a log? Well, if I have an exponential, like that, I can rewrite the exponential in logarithmic form. We always keep the same base. So the base of your exponent is going to be your base of your log. Remember, base to the output equals the input. So the number coming out of the log is actually going to be c. The number going into the log is a. The logarithm function undoes the exponent, and so on. These are inverse functions. So here you plug in c, you get a out. Here you plug in a, you get c out. They perfectly undo each other. Now, you should remember a couple of rules of logs. If you... Oh, we're not there yet. Never mind. So, if I am asked to write like 4 equals 5 to the y in logarithm form, I remember base to the output equals the input. So I'm going to keep the same base. Y is now the number coming out of my log, and 4 is the number going into my log. From there, I can evaluate and solve for y. We will also be asked to write numbers as powers of 10 and e. Remember that ln of x is log base e, which is just a fundamental number. It's like 2.71 blah, 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 blah. It's like pi. Goes on forever. And then if we just write log with no base, that's log base 10 of x. So what if I wanted to write the number 2.4 as 10 to some power? Well, I can rewrite this in terms of x equals log base 10 of 2.4. When I plug that into my calculator, I'll find the answer as to how do I write 2.4 as 10 to a power. If I wanted to write 2.4 as e to a power, I would use log base e, or ln. Now, they are going to give you some simple logarithm problems. This should all be reviewed from pre-calculus. And so we have log base 1/3 of p equals 2. How would I solve for p? Well, in this case, I'm going to take my log and convert back into exponential form. So base to the output equals the input. It looks like p is 1/9. Remember that only positive numbers can be the base, and only positive numbers can go into logarithms, but you can get negative numbers out. Now, this is one form of logarithm problems. The other form, it looks like they're not giving you yet. So that is problem set 9.